Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 17, 2025, about 3 days ago. This paper introduces a plug-and-play diffusion-based outpainting step that reconstructs missing off-frame light sources, letting existing single-image flare removal models work better without retraining, with PSNR on real no-light source images rising from 26.29 dB to 28.41 dB. The paper is titled LightsOut, Diffusion-based Outpainting for Enhanced Lens Flare Removal. And as we will see later, the practical gains for perception tasks are impressive. In short, a multitask regressor predicts off-frame light locations, a low-rank adaptation fine-tuned diffusion inpainting model completes the scene, and the resulting images improve perceptual quality and downstream detection confidence, despite added compute. Also, the authors shared an official GitHub repo. You'll find the full pipeline code in SRC and utils configs and bash scripts, plus ready-to-run inference and custom data tools, an evaluation script, and training scripts for the regression, control, and outpainting modules. Clear setup, dataset preparation, requirements, and sample assets are included. Well, Figure 1 presents the core pipeline and why it helps. The left block predicts off-frame light locations as a compact mask, which gives the method a physically grounded hint about where the missing illumination should be. The center panel shows diffusion outpainting that expands the canvas and restores the bright source so flares become explainable. The right block then feeds this completion to off-the-shelf flare removal models, which produce cleaner crops with fewer residual artifacts. So, Figure 1 showed the pipeline. Figure 2 shows why completing off-frame light sources matters. The top row demonstrates that when the bright source is fully visible, single-image flare removal models clear most artifacts. The bottom row contrasts scenes with missing source context, which causes strong residual streaks and haze because the models cannot infer the true illumination. This gap motivates outpainting to restore the hidden source and stabilize downstream cleanup. Okay, Figure 3 presents the three-stage pipeline in action, which means the system predicts the missing light, paints it back, and then lets a flare remover finish the cleanup. The left panel shows light source prediction that outputs a compact mask of off-frame lights. The center panel runs diffusion inpainting, conditioned on that mask and a caption, with low-rank adaptation and noise reinjection, so boundaries stay coherent. The right panel feeds the outpainted image to a standard single-image flare removal model and crops the clean result. So, with the pipeline established, Table 1 reports head-to-head results across real and synthetic scenes. It shows consistent gains over direct input and diffusion inpainting baselines because reconstructing off-frame lights stabilizes downstream flare removal. On Flare 7K Real without visible light sources, PSNR rises to about 28.4 using the Flare 7K++ model. Perceptual LPIPS, a distance score where lower means more visually similar images, also drops to about 0.040. Similar boosts appear for incomplete light sources and synthetic data, which indicates broad, plug-and-play benefits without retraining. Wrapping up, two takeaways stand out. Reconstructing off-frame light sources with a learned light regressor, plus a low-rank adaptation-tuned diffusion outpainter, makes single-image flare removal reliably stronger, and the plug-and-play design lifts perception without retraining, albeit with extra compute. The broader implication is safer, clearer vision for night driving and robotics. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.